Hi everybody. This is a quick tutorial to tie up some loose ends with vectors as they apply to forces, and this is going to be on the test, so it's pretty straightforward. We talked about it here and there, but I can see some questions on the test coming up that you might not know how to approach unless I give you a process, and like I said, it's not too bad. So I'm going to start off with a very generic problem. I have two vectors, and this could be forces, this could be accelerations, displacement, so it doesn't matter, but generally we apply it to forces. And the two forces are 5 and 20 units. Let's just say newtons for argument's sake, since we're talking about forces. Okay, and I've just drawn them in any random orientation. So what we want to understand is, what could they possibly add up to? Or I could put another way, could they possibly add up to this value? And you'd answer yes or no, and say why. So to do this, we just want to remind ourselves that when you add vectors, 20 plus 5, it doesn't always add up to 25. It can add up to a number of values depending on their angles. So we're going to look at it out of the extreme. So what's the maximum they can add up to? Well, if I have a 20 this way and a 5 pointing in the same direction, okay, they're going to add up to 25. And so what we want to talk about is, what angle are they together apart? What's the angle between them? Or I could attach the 5 right there. So what I want you to understand is, when they're pointing in the same direction, the angle that they occur is at 0 degrees. They're the same, pointing in the same direction, so there's no angle between them. It's not going to be 180 just because I made a straight line here. That's a simple mistake to make. Then I can ask, what's the minimum they could add up to? Well, again, if I have the 20 pointing that way and I have a 5 pointing that way, then we should understand that that adds up to 15. And that occurs when the angle between them is completely opposite of one another. That's 180 degrees. So the question we can then ask is, could they ever add up to 22 units? Well, I've given the two extremes. So I'm going to draw them again, just for illustrative purposes, and to give you an idea pictorially how we're doing it. So here is the maximum when they're like this. And let me make the 21 a little bit longer. Here is the minimum when I put the 5 back on. I'm going to draw a different color. So there's the 20, the green. And when I put the 5 on top of it, right, then our resultant is 15. So what if instead I had my 20 like that, and to it I added the 5? Well, that's going to add somewhere between 25 and 15. Or I could put the 5 like this, or I could put the 5 like that. So there's a lot of different angles that fall between 0 and 180 degrees to which we could add those two. So the long story, or the simple answer to this is, could they add up to 22? You answer that by, does 22 fall between these two extremes? And the answer is yes. So 22 plus 20 plus 25 could all add up to 0. That's one way of looking at it. Or 22 could add up to 22. 22 could be the resultant of 15 and 25. Okay, and then I sketch how they would have to be oriented for this to occur. You don't have to have exact angles. Well, if this example gives us 25 and this example gives us 15, then 22 is going to be closer to this than that. So what I would have is, let's say I draw the 20 horizontally, and then to it I'm going to add a 5 that's not quite horizontal, just slightly up and to the right, so that the resultant is going to be fairly longish. It's going to be greater than 20, but not quite 25. So that could be 22. Next question, could they ever add up to 12 units? Same approach. We look at the two extremes. The two extremes for 20 and 5 are 25 and 15. Does 12 fall between them? The answer is no. Okay, and so you can explain why that, right? 12, right, is does not fall. I'll let you write that out. Does not fall between the two. Okay, so I want you to try these two problems right here. All right, could the three vectors of the following magnitudes, 8, 10, and 15, ever add up to 0? Okay, so give that a shot right now. Pause this, and then I'm going to show you how to solve this, because I want to see what you can figure out on your own. Okay, so the short answer is yes, they could. How are you supposed to figure that out if you weren't sure? You guessed yes, maybe you got it right, or you guessed no, and you got it wrong. There's two ways, there's a number of ways you can do this, but the easiest way to do it is you just take any two of the vectors in question. In this case, I'm just going to choose the 8 and the 10. And I ask myself, could 15 ever add up to 8 and 10? Or could 8 and 10 ever add up to 15? And the answer is yes, because I look at the maximum value of 8 and a 10, that could add up to 18. The minimum value that 8 and 10 could add up to is 2. We don't put negatives here, we're just interested in the magnitude. So does 15 fall between 2 and 18? Yes. And so they could add up to 0. So let me put it another way, pictorially. Okay, so let's say I had a 15 vector pointing that way. If I want to add up to 0, if I want 3 vectors up to 0, I got to form a triangle where the triangle closes on itself so the beginning and the end are the same. Well, if I wanted to, so in other words, 15 would have to be balanced by the 8 and the 10. So the question is, could I make a triangle with a side of 8 and 10 and 15? And the answer is yes. I might have the 8 pointing like that, and I might have the 10 pointing like that. But the point is, I can make a triangle of that. So you already know if I say I have the following sides of a triangle, or I want to make a triangle from the following, could I do that? You should be able to recognize, no, I can't, because 2 and 3 I could put together. There's no way I could ever get it to form another side with a 15. Or, excuse me, be able to add a 15 to it to make another triangle. Let me put it another way. Here's the 15. There's no way I could stretch a 2 and a 3 to close a triangle. So that's the approach that we're using here. So you can do number 2 on your own. The answers are given. Okay, and we can talk about in class when next time we meet as to why that is. Now, there's one little extension to this that I want you to be aware of, and that's called the equilibrant. So since we're talking about forces, and the latest lessons have been where we want the system be in static equilibrium, we want to be able to understand how to add a force to existing vectors so that the vector sum is 0, and that's called equilibrium. Think of an object hanging from a string. Okay, so let's say for this example, I have vector A and vector B pointing in the respective directions. And I want you to draw a vector, 2 vectors, one that shows resultant and then one that shows the equilibrant. An equilibrant is a vector that when added to A and B will make it add up to 0, or put another way, make a triangle. Okay, so here is the easiest approach to doing this. The equilibrant has got to be equal and opposite to the resultant, because the resultant is really just the vector sum of the 2. And so if I have some generic resultant that's pointing this way, it would make sense that to balance that, I'd have to be that way. Or if I take 2 or more vectors and add them up and I see my resultant is this way, then my equilibrant has got to be equal and opposite, because they balance. That's what equilibrant does. So that's how you approach these problems. In the first one, I want to draw the resultant. Please don't mindlessly do something like that. That is wrong. We don't just connect the 2 ends of that. We want to do tip to tail. So these are already connected tail to tail, so I'm going to move A and put it there. So the resultant is from the beginning of B to the end of A. There's my R. That's the sum of those 2. So if I want to balance them, I want an equilibrant that is going to be equal and opposite. So I'm going to put it right there. Try to make this exactly 180 degrees, the same length, and that's my E and R. I know this isn't quite straight, but you get the idea. Okay, go ahead and try B and C on your own. So for B and C, I'm going to move C to down here. There's C. So my resultant is going to be from the beginning of B to the end of C. That's R. So my equilibrant is going to be equal and opposite. There is E. Now I want to show you something about this. I'm going to erase the R in this one right here. So what we're showing is those 3 vectors are adding up to 0. And another way to understand it is if I connect them tip to tail, I should form a triangle. So why don't I do that? I'm going to move B to the end of my equilibrant. So I'm going to leave equilibrant where it is. I'm going to move this vector to right there. Try to draw it pretty much the same. And then I'm going to move C to the end of B. And sure enough, if I'm fairly accurate, I form a triangle. That's how I know they add up to 0. So the last variation of this is instead, if I give you an equilibrant, can we draw the components that make up that equilibrant? Okay, so if this represents some vector, okay, I'll just call it R, how could I put that in equilibrium? And I want to draw components. In other words, two other vectors that will put this in equilibrium. So there's two approaches you could do this. To me, this might be the most straightforward approach. This R can be broken into two components, right? It can be broken into an X and a Y. So that's just another way of expressing R. So if I want to put R in balance, I just need components that are equal and opposite to R's components. So in other words, if this is one component, then the equilibrant component is going to be that way in the opposite direction, and the equilibrant component of this one is going to be down. So these are the two components that will put it in equilibrium. So if I erase this, you can kind of see that if this guy is pushing or pulling up and to the right, I balance the up with a down, and I balance the right with a left. And so those three would form a triangle and add up to 0. So same idea here. If I'm pointing, now I'm going to give you a different approach. For this R, well, I know that the equilibrant has got to be equal and opposite, so I can just draw the components of that. So here is one component, here is the other component. I'm just going to erase this just so we can see it. So, whoops. Now we can see that this, I'll just call this A, and this is B, and R must add up to 0. Okay, so like I said, we can discuss this more if you have any questions, especially before we take the test.